All right, in this video, we continue our study of Fourier series, and our main question in the study of Fourier series is the following. Given a function, f, we can calculate its Fourier series, and under what condition are they considered to be equal? So for this question, we have so far two answers. One is uniform convergence, and the other is L2 convergence. Okay, uniform convergence means roughly speaking, the rate of convergence of Fourier series to the function does not depend on where we are in the interval between negative pi and pi. And L2 convergence means the difference between the Fourier series and the function converges to 0 over the entire domain. Okay, so in this sense, these two types of convergence is called global properties. Okay, and in this video, we study yet another type of convergence, that is pointwise convergence. So in this case, we pick each point at a time and study the convergence of the Fourier series to the function. So we don't care about other points when we study the convergence at a given point. So in this sense, this is a local property as opposed to local property, as opposed to the global property. Okay, let's start. By the way, pointwise convergence means the following. So first, we fix a point in the interval. So this is fixed, given and fixed. Then the partial Fourier sum of the function f at this point converges to f of x 0. In this case, we say the Fourier series converges to the function f at x0. Okay, so this is pointwise convergence. So we can consider this as a sequence of numbers. Okay, sequence of actually can be complex numbers. And so S1, Fx0, and S2, Fx0, and so on. So this is just a sequence of numbers. So this sequence of numbers converges to this number. Okay, so this is pointwise convergence. So convergence at x0. So if this holds for each point, then we say the Fourier series converges pointwise to f of x. Well, first we introduce this interesting theorem by Dubois-Raymond without a proof. Dubois-Raymond. Okay, if f is a continuous function, then its Fourier series may not, okay, this is important, converge pointwise. So actually, we don't need continuity of the function for the pointwise convergence. So what do we really need for pointwise convergence? To answer that, we need to define the notion of piecewise, continuous, and smooth function. Piecewise, continuous, and smooth functions. So that means this. Of course, we consider periodic function, negative pi 2 pi, so period of 2 pi, and we make some sub-intervals, let's say gamma 1, gamma 2, and so on, gamma j, and gamma l, let's say. And since it's a periodic function, we consider gamma L here, and gamma L minus 2 pi here. So in each of the subintervals, the function is continuously differentiable. Okay. So the function may not be continuous in the entire interval, but it is continuous in subintervals. This. And gamma 1 somewhere here, gamma 1 plus 2 pi. So that should be something like this. Okay, so each of these are, by the way, these are open intervals. So gamma j minus 1 to gamma j. In each of these open intervals, the function is continuous and differentiable, and continuously differentiable. So such functions are called piecewise, continuous, and smooth. And we can show that this function is actually uniformly continuous on each of these intervals. And for showing pointwise convergence, we need the following lemma, which I give without proof. And it's called Riemann-Lebesgue lemma. Okay, so let g of x be a function on an interval between a and b, and assume this is continuous, except for finitely many points. So this can be a discontinuous function, but the point of discontinuity are finite. Okay, and also this is assume that this is absolutely integrable. So that means absolute value of g of x integrated over on this interval is finite. Then we have this integral exponential of I lambda x, and g of x dx converges to 0 as lambda goes to a positive or negative infinity. Now we are ready to prove this theorem. Okay, if f is piecewise, continuous, and smooth, then for each x0, the Fourier series converges to not f of x0, because at x0 this function may not be continuous. But this converges to this value, f of x0 minus 0 plus f of x0 plus 0. So what are they? These are actually left limit and the right limit. Okay, f of x0 minus 0 means this limit x going to x0 minus 0. So this x approaches x0 from the left, okay? And similarly, x0 plus 0 means this the right limit. So x approaches x0 from the right, okay? So since this is piecewise continuous and smooth, we have something like this. So we have, let's say this is x0. So if this is within the interval, let's say gamma 1 and gamma 2. So if this is inside the interval where this function is continuously differentiable, then this is equal to, of course, this is equal to f of x0. F of x0. But if this x0 happens to be somewhere here, like gamma 2 itself, then so we take the average between this value and this value. Okay, so this may be this function may be discontinuous at this point in gamma 2, let's say. So we take this value as the left limit and this value as the right limit and take the average, and that is the value to which the Fourier series converges. Okay, let's prove this theorem. Okay, so let Sn of x be the partial Fourier sum of f. That is this. Okay, from negative n to positive n, and Cn, and exponential of ikx. Okay, and Cn is of course the Fourier coefficient of f. And now let's use the Dirichlet kernel to express this Sn. So integral from negative pi to pi, Dirichlet kernel of y minus x0, this x0, and f of y dy. And we can shift this upper and lower limits as long as the difference is 2 pi. So let's shift it to x by x0, pi and x0 plus pi, and the result doesn't change. Okay, and let's change variables. So again, the upper and lower bounds are negative pi and pi, but we shift here. So that is dn of y. So shift by x0 to the negative side. So this becomes f of y x plus y, x0 plus y dy. So if the transition from here to here looks not so obvious, then you can just change the variables like this. So instead of y, we use y prime. That is what is it? Y minus x0. Then if y is equal to x0 minus y minus pi, then y prime becomes negative pi, right? And so this would y prime here. And let's see. So when so y is equal to y prime plus x0, so y prime x plus x0 is here. And then we split this integral into two parts. That is from negative pi to 0, and we again use y instead of y prime. And from 0 to pi. Now recall that the Dirichlet kernel is an even function. So that means dn of negative y is equal to dn of y. Okay. So using this property, change the variables here. So y to negative pi, then we have from 0 to pi, so we swap the upper bound and lower bound and introduce the negative sign. But from here, we have negative sign also, so that will be cancelled, and we have dn y f of x x0 minus y dy. And this one stays the same. Okay, so let's combine them together. So from 0 to pi dn, we use this property here, and dy and f of x0 minus y plus f of x0 plus y and dy. Now, recall that the Dirichlet kernel is normalized. That means if we integrate the Dirichlet kernel itself by itself, then it is 1. Okay, and it is also even function. So this is actually, if we start from 0, then multiply by 2, we have this. Okay, then to this, we multiply to the both sides this f of x0 minus 0 and f of x0 plus 0. So multiply this one to here and here. And let's switch the sides. And so we have, so if this is multiplied to 1, of course we have this. So this is equal to, and 2 times this thing times this. So 1/2 and 2 will be cancelled, and we have dn of y and f of x0 minus 0 plus f of x0 plus 0 dy. So this is equal to this. Okay, now let's subtract this equation from this equation, this Sn equal to this. So that means Sn of x0 minus 1/2 of f x0 minus 0 f x0 plus 0 is equal to integral dn y. Let's split into two parts. That is f of x0 plus y minus f of x0 minus 0 dy, and plus dn y f of x. Wait a minute. This should be minus here. And plus y minus f of x0 plus 0 dy. So if each of these terms converges to 0, then we are done. Okay, that's sufficient. So let's try to do that. Okay, we put this second one as J1 and the first one as J2, and we show only this one converges to 0. Okay, and this one converges to 0. This can be shown in a similar manner, so we just prove only this one. All right. By assumption, f is piecewise continuous and smooth. So because of this, if we take small enough delta, so there exists a delta, such that for all x in x0, between x0 and x0 plus delta, f prime, the derivative, is bounded. Bounded and continuous. Okay, so let's define m delta to be the supremum of the absolute value of f prime, where x is in this interval. And g of y, let's define this function g of y as f of x0 plus y minus f of x0 plus 0. So of course this is the right limit of f at x0. Okay. Okay, then the absolute value of this gy, by the way, y is assumed to be between 0 and delta. Okay, this is ugly. G of y, absolute value, is the integral from 0 to y of f prime of g0 plus t and dt, right? Because, okay, so f prime is the derivative and f g of y is the difference between the function f at this value and this value. So this is it, and this is less than or equal to the integral of the absolute value. This is a consequence of the triangle inequality. But f prime is bounded by m delta, so this is less than or equal to m delta times y, so between 0 and y. So just constant integrated, we get this. Now, let's recall what we wanted to do. Okay, we wanted to show that this J1 converges to 0, and J1 is this times Dirichlet kernel. Okay, so what we want to show is this integral gy converges to 0. And in case you don't remember, the Dirichlet kernel, dn of y is this 1 over 2 pi and sine n plus 1 over 2 y here over sine y over 2. Okay, so this one. Now, we next show that, let's see, integral of g of y over sine y over 2, this one, converges. Okay, so this one is less than or equal to, because of this, m delta and y sine y over 2. And it may not be trivial, but when y goes to 0, then this converges to, I think this converges to 2, right? And otherwise, there is no singular point. So this is actually finite. And next, when y is between delta and pi, we consider this integral from delta and pi and g of y over sine y over 2 dy. And for this y, in this range, we have sine y over 2 is greater than sine delta over 2, which is positive, strictly positive actually. So because of this, we have this is less than or equal to, so replace this one with this one, and we have sine delta over 2 and g of y dy, and this is bounded, this is finite. So together with this result, we can say that from 0 to pi, g of y sine y over 2 is finite. And now we apply the Riemann-Lebesgue lemma to this function. Okay, so if we apply the lemma, so exponential of I, instead of any lambda, but we have n plus 1 over 2 and y, and gy over sine y over 2 dy. So this one converges to 0 as n goes to infinity, right? So, but if we take the imaginary part of this whole function, we have exponential. If we expand this into using the Euler's formula and take only the imaginary part, we have sine n plus 1 over 2y and g of y sine y over 2 dy. So this should also converge to 0, right? But this part divided by 1 over 2 divided by 2 pi is the Dirichlet kernel. So that means Dirichlet kernel y and gy dy converges to 0, and we are done. So we know how pointwise convergence is achieved, and if we define a new function, let's say f tilde of x as this, f of x, where if x is a continuous point, and if f is not continuous at x, then we take the average of the right limit and the left limit. If x is a discontinuous point, then the Fourier series converges to f tilde. Fourier series of f tilde converges to f tilde everywhere. So that's all for this video. Let us summarize what we have learned about various convergences. So if f is continuously differentiable, then we have uniform convergence. And if f is square integrable, or actually we didn't prove this, we proved only for the case where f was a continuous function, then we had L2 convergence. And if f is piecewise continuous and smooth function, we have pointwise convergence. Okay, that's all. See you later.